All right, this is the lecture for section 9.2, the hyperbola, and Jessica's back with us, so we'll go ahead and get started. Jessica, I've already started recording and getting ready to move forward. Glad you made it back in, and if you get kicked out again, just come on back in as you can. Looks like you may be the only one this morning, the only early bird here, besides myself, but maybe a few other people will trickle in as we move past 7 o'clock a little more. I'm going to go ahead and get started. And as usual, Jessica, if you have any questions, you can type them into the chat window or you can raise your hand. Okay, so the objectives for this lesson, of course, this is on the hyperbola. And first we're going to learn how to locate the hyperbola's vertices and foci. It's going to be very much like what we did with the ellipse from 9.1. We'll look at the standard form of the equation for the hyperbola and how to write equations using that standard form. We will learn how to graph hyperbolas centered at the origin, hyperbolas that are not centered at the origin, and all this is going to be very reminiscent of what we did with the ellipse, and then we'll solve one applied problem. Sorry for the delay on the slide change. Okay, so sorry about the delay on the slide change and the fuzziness of the graphics. Like I said, with the ellipse lecture, when I cut and paste from the notes that I type out for y'all and for myself, it tends to make it look fuzzy when I put it on the PowerPoint slide. So maybe we can deal with it. All right. So I wanted to give you an idea of what these hyperbolas look like. So if you'll look at the conic section, actually let me get my pen going here. And I should actually be able to talk a little bit better this morning than I could yesterday afternoon after that being my third class I was teaching for the day. I was a little worn out yesterday evening. Maybe I'll have my language ready to go today. Okay, so let's start by looking at this illustration here of the hyperbola. Remember, we had the little diagram of the different conic sections that are addressed in this text yesterday in the ellipse lecture, and so I found this. I just Googled it and found a really good picture here of the hyperbola conic section. So you can see that we start off with those right cones, and then the plane comes through and cuts both the upper and lower conic sections to create, and I'll just outline as well as I can. Let me get a brighter color here. To create these hyperbola that land the same distance. Well, we'll go into the definition, but there's a center point here where the vertex of the hyperbola lie that same distance as you would expect them to, just from our knowledge of ellipses that we gained in the last lecture. So let's, and then I just have the graphical versions here. We have off to the left, we have two hyperbola, one whose vertices are along the x-axis as well as their foci. And then actually, they're both along the x-axis. I was about to say, and one who's on the y-axis, but we'll see an example of that later on. And then I just wanted to include an example of hyperbolas in architecture. This is the cathedral of, and I'm going to butcher this, Brasilia. And you can see here, if I focus, let me get my pink pen back to draw on this. If I focus on the structure of the building, you can see that as it goes around, this is a cone-shaped building. As you travel around, you've got these opposite pairs of hyperbola, or these hyperbola that have the opposite branches of them. Okay, so we'll go ahead and move forward into the meat of our discussion here today. The hyperbola is the set of points in a plane. The difference, so we're talking about subtraction here. With the ellipses, we had the sum of the distances from two fixed points, and now we're talking about the difference of the distances from two fixed points, and those fixed points are called the same thing, called the foci. And this illustration here shows you those distances we're talking about. So I have a foci here, or a focus here and a focus here. If we're focusing on this rightmost branch of the hyperbola, say this point here, I have this distance and I have this distance from both foci. And as I move along the hyperbola, that difference between the distances is what remains constant. So the difference between that first, let me use colors here, the difference between these two distances ends up being the exact same as the difference between these two distances, and so on and so on. And that's for both branches of the hyperbola. I can go the opposite way and say, okay, I have a distance maybe from here, trying to give some different views, and perhaps here. And the difference between those distances is constant. And it doesn't have to be side specific. I can say the difference between my two orange distances is the same as the difference between my two light blue distances. So it goes across that. The difference between those distances remains constant for this hyperbola to be formed. And we'll see that show up in the standard form for the hyperbola. So the line through the foci intersects the hyperbola at 2 points. So the line through the foci, let me get a different color and grab that orange again, and we'll look at this topmost illustration. The line through the foci intersects the hyperbola at 2 points. And those 2 points, as you would suspect, are called the vertices. The line segment that joins the vertices, right here, that is called the transverse axis. We only have one axis with these hyperbolae, transverse axis. So unlike the ellipse where we had two axes, we had the major and the minor, here we just have the one because these hyperbola don't connect with each other. So we have the transverse axis there. And then the midpoint of the transverse axis, as you would suspect, is called the center. Okay, Jessica, I don't know how easy it is for you to give me a green check, but if this seems to make sense so far, if you can. Yeah, very good. Excellent. I'm glad your phone will allow you to do that. I'm going to go ahead and move forward. Okay, I'm grabbing a sip of coffee. Hang on just a second. Okay, the standard forms of the equations of hyperbola are listed below here. So here's what I want to point out. You have hyperbola whose transverse axis is horizontal. When that is the case, you will see the x squared term listed first. Now notice a squared is always your larger value, and that's always going to be listed first. We have to pay attention to the order of the terms because we're subtracting this time. So those A's and B's we can't shift the position of them, or it becomes the transverse axis shifts to the other axis or in the other direction if it's not centered at the origin. But I want you to notice that your larger value or your a squared value or a value is always going to be with the first term, whether it's x or y. So I'll also point out that when your transverse axis is vertical or in the y direction, I went all the way to the focus on that. Let me delete that because it goes from vertex to vertex, not between the foci. So vertex to vertex. So when that transverse axis is vertical, you'll notice that we have our y squared term first. And that's easy to remember because the y direction is vertical and the x direction is horizontal. So whatever term, x or y, is listed first, that's going to clue you in a little bit as to what your hyperbola will look like. So all the other parts, besides the fact that we're dealing with a difference here, or subtraction of these distances, is the same as you would expect with the ellipse. Before we move forward, I want to point out that the vertices are a units from the center. So this value here is positive a, and that is, well, the value is a, but it goes in the negative direction, so that's negative a. Same thing here, we have a and then negative a there. And then the foci are C units from the center. So let me point those out to you as well. So from here to here, that is C units, as well as going in the opposite direction. Still C units, but I put negative C to denote going downward. And same thing here. Let me go below. Okay, so that's C. And then this is, it's so hard to draw those upside down, those braces, negative C. All right, and then, you know, like we had in the ellipse equation, there's a lot of fancy simplification that happens, and I'm not going to go through that this morning at all, but we end up with, and this will be the form that we'll use, basically that distance between the center and the foci, when you square that, that is equal to the distance between the center and the vertex squared plus the center, and this B value is the other edge of the rectangle, and that'll if we had the ellipse, we'd be talking about that as endpoints. But we'll see later where that B comes into play. It comes when you're in play when you're graphing these things. Okay, so cool so far, Jessica? And I really appreciate you getting up this early and meeting me. Excellent, we'll move forward. It's nice to have at least one person to give feedback. I don't know if you heard me as the slide was changing, my microphone cuts out, I think, but I was saying thank you so much for joining me. It's nice to have at least one person to give me some feedback on this. No choice, a 3-year-old. This is probably about the only time you have that's maybe quiet. However, your 3-year-old may be up with you right now. Those 3-year-olds can be tenacious. Or maybe you're saying she's up. So she's learning about hyperbola as well, or perhaps maybe 6 a.m. every day. Goodness. I'm usually the first one up in our house, and I usually get up around 4 a.m. And the dogs got up early with me this morning because I was making too much noise. My husband just turned over. You'll probably hear him coming through here in a minute, getting off on his way to work. I'm still in my jammies, so absolutely no camera today. All right, so let's take a look at these two examples here. We're asked in this particular problem to find the vertices and the foci of these hyperbola. Now notice the difference they look very similar, but the difference in these two is that with A, we are starting with an x square term, and with B, we're starting with a y square term. So you can already see that with A, I'm going to have a transverse axis that's horizontal. With B, I'm going to have a transverse axis that's vertical, and these are the pictures below the graphs of these particular hyperbola. So we're not asked to graph them in this one. That comes up in just a moment. We're just asked to find the vertices and the foci so that we can build up to understanding how to graph these things. Okay, so to find the vertices, the vertices are given by the value A. Well, we know, according to our equation here, that A squared is equal to 25. That means A is going to be equal to positive or negative 5 after we take the square root of both sides. So that tells me that my vertices are located at negative 5, 0, and 5, 0, right here and right here. And don't forget, the vertices land on the hyperbola. The foci lie outside of those vertices, or further away from the center than the hyperbola rests. So we'll go ahead and find the foci now. And that's where that little piece of information on the last slide comes into play. This piece of information that C squared is equal to A squared plus B squared. So in this case, C squared is equal to A squared is 25 from our equation, and B squared is 16 from our equation. Remember, A is always in the first slot, B is always in the second, no matter what variable is in the numerator there. So we have that c squared is equal to 41. When we take the square root of both sides, I get that. I'm getting a little faster with the pen here, getting back into my groove. We get that c is equal to the positive and negative square root of 41. I'm just going to give a decimal estimation of that. That is approximately positive negative 6.4. So our foci are located at negative 6.40 and positive 6.40. So I'll just graph those for you. Roughly here and here. Okay, so that's all this particular problem asks us to do, is just find the vertices and the foci. So I'm going to go ahead and move on to the other ones. You good with that first one, Jessica? Excellent. Thank you. Okay. So once again, let me remind you that our transverse axis is horizontal here because y squared is the leading term. All right, so our vertices, once again, we're focusing on the A. A squared is still 25 here because it's always the first term there that your A value is gotten from. So A is equal to positive negative 5 again. Okay, so here's where the difference is. And I'm going to do this one in a different color. So I came back and I took the square root of both sides. My vertices are located at 0, negative 5, and 0, 5 because we're in the vertical direction. So here, or our transverse axis is vertical, there and there. So that's why I put the value of A in the Y coordinate spot there. All right, foci. We still have c squared equals a squared plus b squared. So my c squared is equal to, once again, 25 plus 16. C squared is 41. C is equal to the positive negative square root 41. C is approximately positive negative 6.4. Once again, the difference here is that we're working in the vertical direction. So my foci this time live at 0, negative 6.4, and 0, 6.4. So about right here and right here. All right. Green check if you're ready to move on, Jessica. Excellent. Moving forward. Okay, this next problem, okay. Sorry, my tablet was acting crazy on me there for a moment. Okay, so find the standard form of the equation. So now, instead of starting with the equation and locating the vertices and the foci, we're going to start with the foci and the vertices and work backwards to write the equation of the hyperbola. So the first thing I'll point out to you about this problem is, notice your foci and the vertices that are given are all y-intercepts. They are all y-intercepts, which means my transverse axis, I'll just call that TA, not TNA, haha, but TA. Your transverse axis is going to be vertical. You're supposed to laugh out loud at my TNA joke, Jessica. I'm just kidding. Okay, so the form that we are going, thank you. The form that we're going to try to write this equation in will be y squared over a squared minus x squared over b squared equals 1 because of the vertical transverse axis. That's why the y is leading this time. Okay, so I will just point out that the distance from the center to the vertex is 3 units. And I got that because I knew that's supposed to be a double arrow there. That's pitiful. A is equal to positive and negative 3. So 3 units in both directions. Since A is equal to positive and negative 3, A squared is equal to, so if I come back and I square both of these, I end up with A being equal to positive, I'm sorry, not positive and negative, the negative squares away. A squared is equal to 9. So far, let's see, I'll put my final equation down here. So far, this is what we know. Y squared divided by something minus x squared divided by something is going to equal 1. Well, we've just figured out the first something, the a squared, is 9. Now all we need to do is figure out what b squared is so that we can finish off the equation. Well, the only way we have of working with b squared is from that little relationship that we were given, that the distance to the foci squared is equal to distance to the vertices squared plus distance to the other side of the rectangle squared. Once again, that rectangle makes sense once we start talking about graphing it. All right, so we can get a c squared value because we know where our foci live. So our foci are 5 units in both directions, so this is positive or negative 5 squared equals positive negative 3 squared plus b squared. So we'll solve for b this time. 25 equals 9 plus b squared. Subtract 9 from both sides. And we get a nice, neat 16 equals b squared. Now we could go further and talk about what b is, but that's the important part that we need. B squared is 16. But just for the curious, and I'm sure it's not anything to be too curious about because you probably already know it, b is equal to positive negative 4. And that'll, once again, that'll be useful when we're graphing. All right, so we've got the equation for this particular hyperbola written. You good to go? Excellent. Another sip of coffee. Okay, so now we're moving into the details of graphing these things. And they're a little bit more involved than graphing the ellipse. All right, let me get a colored pen here and grab pink. I'm liking this pink this morning for some reason. Normally I'm not a pink kind of gal, but it's working for me. All right, so the asymptotes of a hyperbola. So we learned about asymptotes back in college algebra. These are invisible lines that the graph of your equation approaches but never actually gets to. So if you look below, these diagonals are serving as asymptotes to the hyperbola. Same thing here. So those are asymptotes. And to graph hyperbolas, we've got to know where those asymptotes live. So it is important for us to know how to write the equations of those lines. And you always draw them with dotted lines. Same thing with the guiding rectangle when you're graphing these things. The only thing you graph as solid is the actual hyperbola. So I'll just point out that the first one we're talking about is when your x squared term is leading. So this is when your transverse axis is horizontal. When the transverse axis is horizontal, the equations for the asymptotes are, I would write this as y equals positive or negative b over a times x. So that b over a is the slope of those lines there. So they just split it into two different equations, which is fine. And the next thing, the next little item to look at here is when y squared is your leading term. Don't forget that means your transverse axis is vertical. Notice it just flip-flops the numerator and the denominator of your slope there. And this is some nasty mathematics, where all this comes from too. It's simplifying these equations here. And I'll spare you the nasty mathematics. So positive and negative a over b times x are the equations of, you're welcome, Jessica. A over b times x are the equations of these particular asymptotes. So there we go. Let me fill in that blank for you. I'm sure you can fill it in by yourself by now. As x and y get larger, the two branches of the graph of the hyperbola approach a pair of intersecting straight lines called asymptotes. When I taught high school, I used to always try to make them giggle by spelling it asymptotes. And then I'd be really worried about if I was going to get calls from parents because of my curse words. Never happened, and I breathed a deep sigh of relief after my 2 years of teaching high school. I was happy to move into teaching college, so I don't have to behave myself quite as much. Okay, I'm going to go ahead and move forward. You didn't have any questions on that last one, did you? I can go back if you need for me to. Okay, excellent. Okay, so now the steps to graphing these things. So you can see this is that same diagram here, and it's got your asymptotes labeled. It has the equations of your hyperbola labeled for you. So this is a really nice illustration to come back to, just to get an overall picture of what's going on with these hyperbola. Okay, so your first step, and I'll go through the steps, and then of course we're going to go through graphing one of these things. So the first thing you're going to do is locate the vertices. And Jessica, I'll just tell you, my hubby's about to make his breakfast shake. He's going to turn the blender on here in a second, so it won't take him long. If I cut out for a moment, you hear a blender in the background, that's what's going on. Okay, so you're going to locate the vertices first. You're going to use dashed lines to draw the rectangle centered at the origin with sides parallel to the axes, crossing one axis at positive and negative A, and the other axis at positive and negative B. So if you look here, this is that rectangle I was talking about earlier. We have these parallel sides going through the vertices, and then the parallel sides going through, if we had an ellipse, what would be our endpoint? That sort of centers us up to begin drawing or graphing our hyperbola. Blender time. Okay. Breakfast is done. Okay, use dashed lines to draw the diagonals or the asymptotes of this rectangle and extend them to obtain, okay, so the diagonals to obtain the asymptotes. Draw the two branches of the hyperbola by starting at each vertex and approaching the asymptotes. So just on the rightmost diagram up there, the first step is to locate your vertices. Then you're going to draw your rectangle. Then you'll actually graph your asymptotes. And then once you get that, you'll start at the vertex and draw that hyperbola as it approaches the asymptotes both ways, and then both sides. Okay, so we'll go through this process now, and hopefully everything will be clear as mud. Okay. All right, here we go. So, step one, locating your vertices. So I'll just point out here, don't forget your vertices are always given by that A value, or that's A squared, but they're given by the A value. So since A squared is equal to 36, we take the square root of both sides. A is equal to positive and negative 6. So my vertices are located, okay, don't forget, this particular transverse axis is horizontal. So my vertices are going to be located in my X values. So these are negative 6, 0, and 6, 0, right here and here. Now I'm ready to draw my rectangle, but to draw my rectangle, I need to know where my B values lie as well. Let me change colors. So my B squared is 9. So since B squared is 9, take square root of both sides, B is equal, that's an equal sign, to positive negative 3. These are in the vertical direction. So I have my B points, or in this case my y-intercepts, at 0, negative 3, and 0, 3. So I'm just going to mark those before I draw my rectangle. And then I'm going to come back and dot in my rectangle just to give me guidelines. There we go. Next step is to draw the extended diagonals. Well, I can go ahead and find the equation of those asymptotes to be extra special on point with drawing these. So there's my center point. And we are told that because my x squared term is leading, I know that the equation of those diagonals are y equals positive and negative b over a times x. So positive and negative b over a are my slopes of those diagonal lines. So in this case, I have y equals positive and negative 3 over 6x, which means I have y equals positive negative 1/2 x. So up 1, right 2. Up 1, right 2, put a point. Up 1, right 2, up 1, right 2. You can do that as many times as your little heart desires. And then I also have up 1, left 2. Up 1, left 2. Up 1, left 2. So I have this asymptote. Actually, I don't need arrows on those. Not necessary. And I have this asymptote. Sorry, my dotted lines are more like squiggles. All right. Step 4, draw the 2 branches. So now we're ready to actually graph our parabola. Don't forget, these parabola live in the horizontal, or they have the horizontal transverse axis. So here's that horizontal. Let me get a different color for the parabola. I'll get a bright green. Here's my transverse axis between my vertices. Okay, so to draw my parabola, I start at the vertex and just move towards, but don't cross, the asymptote, both directions there. And then I come back and do the same thing on the other side. So we've got the hyperbola graphed here. Now we are asked, what are the foci? So foci, I'm going to start out with c squared equals a squared plus b squared, because it's the only relationship that I have to the foci with the vertices and the b values there. So in this case, c squared is equal to 36 plus 9. C squared is equal to 45. Take the square root of both sides. So c is equal to positive negative square root 45. You could simplify that if you wanted to have a simplified square root. Since we're graphing, I'm going to go ahead and put in terms of, hang on just a second, Jessica, lunch today? Okay. Put these in decimals since we're graphing. So that's positive negative 6.4, approximately. That's what the wavy equal sign is approximately. So since I'm dealing with a horizontal transverse axis, those foci are going to show up on the x-axis, so the coordinates for them are negative 6.40 and positive 6.40. So right here, 6.4, maybe about right here, and here. What are the equations of the asymptotes? Luckily, we've already done that work. Y equals, now in my math lab, you'll have to split them up into 2 equations, but I'm just going to write positive negative 1/2 x. You good with the graphing, Jessica? At least the graphing when it's centered at the origin. Excellent. We'll move forward. Just so you know, we've only got 3 slides left. And this next slide is just looking at information, kind of putting it all together here with hyperbola that are not centered at the origin. So just as you would suspect, exactly like we had with ellipses, we are now centered at HK. H is always, 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 it travels with the x term. And it's subtraction. You're finding the difference between those. So notice here, even when our transverse axis is flipped, that h is still listed with the x term. And the k, obviously, is listed with the y term. So your center shows up at HK. Don't forget, minus is in the form here. So if you see plus, for example, say I have x minus 2 squared over whatever a squared is, we're not focusing on that part right now, minus y plus 3 squared over b squared equals 1. I would rewrite that equation to locate my center as x minus 2 squared over a squared minus y minus negative 3 squared over b squared equals 1. So my HK in this case would be 2, negative 3, my center there. So I just wanted to point that out to you. And it's the same no matter how your transverse axis is situated, vertically or horizontally. All right. So let's graph one of these, and then we'll have an application problem, and then we're done. Okay. So I chose a little more difficult problem to do here in that your equation is not given to you in standard form. So you may have to get your equation into standard form before you can even start moving through the steps of graphing these things. Okay, so I'm going to take you through completing the square for the x and the y terms here. So we start out with 4, and I'm going to try to squeeze all this in this little space I left myself here, minus 24x minus 9y squared minus 90y minus 153 equals 0. So the first thing I want to do is group into binomials. I have my x's here, and then I'll be adding my y's. The reason I put the plus there is because I kept that negative with the y squared term. And I'm going to want to move that 153 over to the other side by adding 153 to both sides. Okay, so here's what we look like. 4x squared minus 24x plus negative 9y squared minus 90y equals positive 153. And now I'm ready to factor and then start the process of completing the square. So with these first two terms here, my x squared, my x term, I'm going to factor out a 4. And I'm left with x squared minus 6x. I'm going to leave a blank for completing the square there. So that's what that space is for. And then with this next set of terms, I'm going to factor out a negative 9 because I never want my leading term negative, so I want to factor it out. And I have y squared plus 10y. I'm going to leave a space to complete the square, and that equals 153. Okay, so coming back to complete the square. Remember, to complete the square, you need to add on, so completing the square, you're going to add on b over 2 squared. And my b is always with my x term. So in this case, I have plus negative 6 over 2 squared. And in this case, I have plus 10 over 2 squared. Okay, so I'm just going to simplify that. Oh, and I need to add them onto the other side. I can't. Actually, I'm going to hold off adding those to the opposite side for just a moment, but you would add those onto the other side. I'm holding off because there's some explanation that needs to be done there. So let me just simplify this, make it look a little nicer. 4 times x squared minus 6x, that negative gets squared away, so that's just negative 3 squared, which is positive 9, minus 9 times y squared plus 10y plus 25, 5 squared there, equals, okay, so let's go back and add those values to 153. So here, let me get a different colored pen. Here, I added a 9, but I added a 9 inside the parentheses that gets multiplied with a 4. This is why I wanted to wait, because I'm going to add a 36 there, 9 times 4. Same thing here. I have a 25 inside, but that gets multiplied with a negative 9, so I'm actually going to subtract 9 times 25, which is 225. So 153 plus 36 minus 225 lands us at negative 36. Let me stop there. Did that make sense, what I just did? Jessica, you still with me? Okay, are you good to go? Can you give me a green check or red X? Or you can type it. I saw you typing. Good to go. Okay, good. I'm glad that that didn't look like a bunch of witchery happening there. All right, so now, since I can write these as perfect square trinomials, I can rewrite them in their factored form, which is where we're trying to move towards with completing a square. We're trying to get it to look like that standard form of the equation of for the hyperbola. So this is 4 times x minus 3 squared minus 9 times y plus 5 squared equals negative 36. Well, we know the standard form of our equation is equal to 1, so I'm going to divide every term by negative 36. I knew I'd run out of room. And I finally end up, well, let me go and show you the math here. Negative 36 goes into, I'm sorry, 9 goes into 36. 4 goes into, my bad, 4 goes into 4 once, and it goes into 36 negative 9 times. Negative 9 goes into negative 9 once, and into negative 36 positive 4 times. Negative 36 divided by negative 36 is just 1. Okay, so I'm just going to rewrite what I have happening here. I now have, okay, so let me stop. This negative right here in the denominator can translate out to call that whole term negative, because you've got a positive numerator being divided by a negative denominator. So I'm going to rewrite as, let me see if I'm going to have room. I'll write it up at the top of this graph here, so. Because this graph, once we once we situated it, is actually going to have a vertical transverse axis. So here's where we are. Negative x minus 3 squared divided by 9 plus y plus 5 squared divided by 4, and that equals 1. However, this is still not in standard form. I need to flip-flop my terms. I don't want to lead with a negative term, so I'm going to flip-flop these and finally end up with my standard form of my equation, which is, I'm going to delete this at the top corner so I have room. Okay. So my standard form is y plus 5 squared divided by 4 minus x minus 3 squared divided by 9, and that equals 1. And I'll just point out that that y plus 5 is really y minus negative 5. So from that, I get that I have a center of 3, positive 3, with my x value there, negative 5. So my center is 3, negative 5. And I can go ahead and graph that. 1, 2, 3, down 5. Here's my center. All right. Now we're actually, oh, that should say vertices, not vertices. I don't even know what a vertices is. Okay, so moving forward, we want to locate the vertices. So I have my equation, y plus 5 squared over 4 minus x minus 3 squared over 9 equals 1. Remember, your a value is always with your x. So when I was have to clock into work. Now have a good day. You too. Thank you for coming, Jessica. Okay, so my a value, don't forget, it always sits in the first slot, no matter if that's a y or an x term. So a squared is equal to 4, which means a is positive and negative 2. Now, these aren't the points 0, negative 2, and 0, 2, or 2, negative 2, 0, 2, 0. This means that because our transverse axis is vertical, and we're talking about the vertices, our vertices are located 2 units above and below the center. So if I go to my center and go 2 units above, 2 units below, there are my vertices. And to answer what the vertices are, we can look at the mathematics within the coordinates here. So for 2 above, And the above and the below is happening on the y. That's the vertical direction. So our center is at 3, -5. And to find where the upper vertex is located, I want to add 2 to the y value. So I get the point 3, -3. And that is this vertex right there. I just darkened it in. Let me make it a different color so you can, or I'll put the green dot in the center. This vertex right there. All right, and then we have the one that rests 2 below. Once again, happening in the y direction, so 3, -5. This time I'm going to subtract 2. And I have 3, -7, which is this vertex right here. Okay, so we have our vertices drawn now, or graph. Now we want to draw that rectangle. Well, we need to know our B value, so how far away in the opposite direction from the center do the sides of that rectangle lie? Okay, so in this case, B squared is equal to 9. So B is equal to +3. That means that the sides are located 3 units left and right of center. So 3 units to the left, 3 units to the right. And I'll just once again show you the mathematics within the coordinate. So 3 to the right. This is happening on the x value this time, 3. +3. -5 gives us 6, -5, which is this point here. Okay? And 3 to the left. I have 3 -3 this time. -5. And that gives me 0, -5. And that is this point there. Okay, so I'm ready to draw my rectangle. That was a lot of work just to draw a rectangle, huh? Okay. And I'm just going to darken in my vertices. Okay. Now that I have all that work done, I am ready to draw my extended diagonal. So I'll draw them first, and then I'll come back and figure the equations for those lines. And it's a little more involved since we're not centered at the origin. So you have to use the point slope form to get the equation of that line. And I'll show you that here. All right, so I've got my asymptotes drawn, and now I want to find the equation of those asymptotes. So I start out with the fact that the slope of those asymptotes is positive, negative, A over B. It's A over B because our transverse axis is vertical. So in this case, an X, that's the equation of it. So in this case, I have Y equals positive or negative 2/3 X. That just gives me the slope of those lines. I'm not centered at the origin, so that is not the full equation of the asymptote. That I have to use that to get the equation. So one point that I know this equation goes through is the center, or this line goes through, and that's 3, -5. So I can use the point slope form of for the equation of a line, which is y minus y1 equals m times x minus x1, to write the equations of the asymptotes. So for the first time, I'll do a first run through, I'll do positive 2/3 as my slope, and then I'll do negative 2/3. All right, so y minus -5 equals positive 2/3 x minus 3. And then I just have to simplify. Y plus 5 equals 2/3 x minus 2 times -3 is -6 divided by 3 is -2. I'm going to subtract 5 from both sides. And I get y equals 2/3 x minus 7. That is, let me get a different color, get yellow. That's this asymptote. And notice it goes through -7 at, as its y-intercept. On the y-axis, it goes through -7. So here's your y-intercept right here. All right, so I need to do the other one using the negative slope. So y minus -5 equals -2/3 x times x minus 3. Y plus 5 equals negative, oops, hang on, I wasn't supposed to put an x there. Okay. Y equals -2/3 x plus 2 this time. Subtract 5 off of both sides. And I get y is -2/3 x minus 3. And let me do another color. So that's this asymptote. And once again, you can see that it crosses the y-axis at -3. So there are the equations of the asymptotes. So actually, we have just answered that last question there. Okay, what are the vertices? We've already got the answer to that question, so I'll just rewrite it over here. Oh, draw the hyperbola. I forgot to draw that. Let me go back and draw the hyperbola. So once again, our transverse axis is vertical. I'm just going to dot that in there. So my hyperbola start at my vertex and approach my asymptotes. So there's my hyperbola. The vertices are 3, -3, and 3, -7. My foci I get from c squared equals a squared plus b squared. C squared is equal to, okay, so my A is 4, or A squared is 4, plus 9 is my B squared. C squared is 13. C is the positive and negative square root of 13, which is approximately positive negative 3.6. I'll go ahead and graph those. And it's 3.6 away from the center. So let me actually show you the math before we do that. Once again, it's in the vertical direction, so it's going to be on the y coordinate. So negative 5 plus 3.6, which gives us 3, negative 1.4. And then we have 3, negative 5 minus 3.6, which gives us 3, negative 8.6. So 3, negative 1.4 is about right here. And then 3, negative 8.6, so 5, 6, 7, 8.6 is about right here. I think that's 9.6, about right here. It's hard to be so detailed with this pen. Okay, so we've drawn it. We've answered. Oh, let me point out that we've answered all the questions. So the foci. There are the foci. We have our vertices, and we have the equations for our asymptotes. Vertices. All right. Last question, or last problem to work. It's an application problem. Okay, so first of all, up to the top left, I just wanted to show you some practical applications of hyperbola. These come from your book. So the shape of a sonic boom actually makes a hyperbola there, and you can see that the cut of the cone happens with the surface of the Earth there. I thought that was kind of cool. And I also thought it was cool that the orbit of comets is in a hyperbola in regards to how it passes the sun. So, you know, just a little bit of practical application. Now we have this last problem to work through. A good way to start a word problem is to read it. So, an explosion is recorded by 2 microphones that are 2 miles apart. Microphone M1 receives the sound 3 seconds before microphone M2. Assuming sound travels at 1,100 feet per second, determine the possible actions of the explosion relative to the location of the microphones. So, looking at this drawing up here, because the second microphone picked the explosion up 3 seconds after the first, I can assume that the distance from the explosion to the second microphone is 3,300 feet, because 3 seconds times 1,000 feet per second gives me 3,300 feet. Also, we know that the microphones are 2 miles apart. Well, 1 mile, I'll write this at the top, 1 mile is equal to 5,280 feet. So I can situate my foci, let me get a different color. I can situate my foci at negative 5,280 feet and positive 5,280 feet, since they're 2 miles apart, considering the origin, the center between my 2 microphones. So we situated this on the graph to be nice and neat for us. I think that's all I want to point out about the diagram before I start working. Okay, so to write the equation of this hyperbola, we have that we are working towards x squared over a squared minus y squared over b squared equals 1. We are using this form of the equation because I know the way that this hyperbola is drawn and is situated. Since my foci are on the x-axis, I have a horizontal transverse axis. So that's why my x squared term is going to come first. And I want to point out to you that the difference between the distances from the definition of a hyperbola in this case is 3,300 feet, because I knew that they were 3 seconds apart. Thus, 2a, which we defined back with ellipses, 2a is equal to 3,300 feet, which means a is equal to 1,650. So just off to the side, I know I'm working towards x squared divided by something minus y squared divided by something equals 1. That something that is a squared, I have a here, so let me grab a different color and square it. Since a is 1,650, a squared is equal to, and I've already done this math, 2,722,500. So 2,722,500 is my a squared value. All right. So moving further, now I need to figure out what my b square value is, and I'll have the equation of that hyperbola. Well, the only other piece of information that I have is about my foci. Well, the way, and here's what I know about my foci. I know that my foci have a C value of positive and negative 5,280 because they lie 5,280 feet in both directions. The only thing that I have to relate all these pieces of information is that C squared is equal to A squared plus B squared. C squared, 5,280 squared, is equal to 1,650 squared plus B squared. 5,280 squared is 878,400, and that equals that 2,722,500 plus B squared. Subtract 2,722,500 from both sides, and I get that B squared is 25,155,900. That's B squared. And that is the value that we need to finish off writing the equation. Hang on. Right here. And we could go further and say what b is and take the square root of that, but it's not necessary for this problem. So this is 25,155,900. And, you know, just looking at this, I know that my explosion happens closer. Let's see, determine the possible locations of the explosion relative to the location of the microphone. My possible location is that I lie much closer to microphone 1 than I do microphone 2, because it had to travel, the sound had to travel for 3 seconds to reach microphone 2. And just situated with my parabola, I could start plugging in values and receiving them out and showing how it lives closer to microphone 1 than microphone 2. And that's it. So let me make the announcement. And just to clarify, this is announcement for spring 2015. So when I reuse this, hello? When I reuse this recording, these won't be the correct dates, and there are no live lectures once they're recorded, because this is a lot of work. So I just record them and get them transcribed to use for the next semesters. But for spring 2015, the next lecture will be next Wednesday, January 28th at 5 p.m., and that is going to cover the parabola. I hope to see you there. Y'all have a wonderful day.